Okay, thank you for your introduction. In this talk, I will introduce a tool that's called ET, which is for the bounded validation of SMT servers. And I will also send you home with some fresh perspectives on testing software in general. And this is joint work with Zhendong. So a very brief introduction to SMT I will repeat. So an SMT server is essentially a tool that, given a first-order logic formula and with some background theory, will return set if that formula is satisfiable and unset if it's not satisfiable. SMT servers realize much of the foundations for our software research, and these days several large-scale applications in industry depend on them. Because SMT solvers are so important, bugs in them can be critical. So for example, if we have a bug on a satisfiable formula we get answered, that's a critical soundness bug. If SMT solvers have many critical soundness bugs, their unsoundness can propagate, and so we can no longer trust the tools that build on SMT solvers. And likewise, as SMT servers are usually at the heart of software, if they have poor performance or are incomplete, that will also affect the client applications, and so those will also be slow on terminating. So SMT servers should be correct and performant. One of the major ways of ensuring correctness and performance of SMT servers is SMT server testing. And so there have been many works, many papers, and researchers have been devising techniques for doing that. And also, they ran large-scale bug hunting campaigns on SMT servers, resulting in over 3,500 bugs with 2,500 fixes in the SMT servers. Given such a major effort, the main question that we can ask here is, have we tested enough? Are the solvers actually improving? In this work, we make three main contributions to approach these questions. The first one is a validation campaign on the SMT servers. We make a bounded validation of SMT servers Z3 and CVC4, and by that we find over 100 bugs. And we also increase confidence in the absence of bugs in important theories. As a second contribution, we investigate the evolution of SMT servers with respect to correctness and also performance. And for correctness, we observed significant improvements, which means recent releases of Z3 and CVC4 no longer have bugs in most theories. And finally, we also propose a tool with which we do all of this, called ET, which allows us bounded validation of software and produces, if we find bugs with it, it produces very small bugs. And this generic works with any context-free grammar. So let's revisit the central question of this talk. Have we tested the SMT solvers enough? So let me, before really going into the detail of this question, let me first tell you why the existing testers cannot tell you an answer to this question. So first of all, they are unsystematic. They produce large bug triggers, and they're random, scattering around a big space of formulas. And so they don't provide any guarantees. If we stop fuzzing, we don't know whether if we then don't find bugs, we don't know whether there are actually no bugs or whether we were just purely out of luck. And they miss simple bugs, such as this one, for example. The formula we see here just has a single variable a and implements a very simple trigonometric equation, tangent double sine of a. If we plug in -1 for a, then so we get a value roughly at -0.9, which is greater than -1. So this formula should be satisfiable. But if we give this formula to CVC4, the solver will return unset, which indicates a critical soundness bug. What can we learn from such small bugs? So there's an empirical law called the small scope hypothesis on software testing. This has been established by Daniel Jackson from MIT. The small scope hypothesis says that the most interesting behavior of software is actually observable on small inputs. So the question here is, does this also hold for SMT solvers? Yes, it does. And we have established that in our earlier OOPSLA 2020 paper, where we investigated 1,000 bugs and saw that the triggers for these bugs are smaller than 300 bytes. So it holds. How can we exploit this insight? The idea is to enumerate inputs from the smallest to increasingly larger inputs using context-free grammars. And we get many benefits by this. First of all, it's systematic. If we find bugs, they are small. It provides bounded guarantees on the input spaces that we test. And this way, along with the small scope hypothesis, we can judge the evolution of SMT solvers. We integrate this idea in a tool that we call ET, the enumerative tester, or extraterrestrial. So ET works as follows. It takes a grammar, it takes a desired number of tests, and then we first compile this grammar to algebraic data types. And then we couple it with a testing library called feed in Haskell. And feed will realize a random access to the grammar, essentially, and produce smallest formulas to the bigger ones. So if we have n, then it will produce us the n smallest formulas. And we couple this with a differential oracle to stress test the solvers against each other. So have we tested enough? So now, finally, we have a criterion by which we can judge what enough means. Enough means no bugs found by ET. Under two assumptions. The first one is all bugs have small triggers, which is strongly according to the small scope hypothesis. The second assumption is that we can describe the SMT theories with grammars, context-free grammars. And we have devised eight such grammars for each of the official theories, including core, integers, reals, bit vectors, and so on. With that, we have conducted a validation campaign, and then we found over 102 bugs, out of which 84 were confirmed and 40 were fixed. So many of these bugs are actually performance bugs, and we will see why that is later. But there are also some soundness and crash bugs and invalid model bugs. But perhaps more important than these bug findings is the increased confidence that we now have in the SMT solvers. By enumerating the smallest tests, we can be way more confident that SMT solvers no longer have bugs on these simple bugs on these important theories. As I said, performance bugs are especially, or approaches especially suitable for performance bugs. And here I want to show you a quick example. So we have this super small formula. And if we just give it to Z3, Z3 will just not solve it. It will just hang. The reason why this is it's very confusing. It's related to this expression isInt, which returns true if the child is essentially an integer expression and false otherwise. And so this Z3 actually gets stuck in an infinite loop if in this expression there are only integer variables, which as is the case here. The point that I want to drive home here is that the small bug trigger, and this was actually a real finding of our testing tool ET, unreduced, it enables us to track down such issues, which would be way harder otherwise. Another question that we can now attempt is whether SMT solvers have become better. And let's start with correctness here. We stacked up releases of Z3 and CVC4 from November 2016 to March 2024. That's in total 61 releases. And you see two plots here, one for Z3 and the other one for CVC4. And the x-axis shows you the releases from old to new. And so the y-axis determines the number of bugs that have been triggered. And we run our tool ET on all the grammars which we indicate by the different colors on 1 million test cases. So if we did that for Z3, we observed that initially Z3 has many bugs in many theories, but then it drops down. And maybe most strikingly, Z3 has no bugs in the latest releases anymore. And for CVC5, we can observe a similar to early drops. And if we look at the latest release, we just see bugs in only a single theory. And so if we also looked at the kinds of bugs that we find, and we saw that after some specific versions of the solvers, we do not find any soundness bugs anymore. And so the point I want to make here is that Z3 and CVC5's reliability and correctness had improved significantly over the years. So similar as for the correctness experiment, we also investigated performance evolution. We did that for short timeouts to investigate aggregating effects for when we have many solver calls, and long timeouts to indicate performance regressions. So the first plot here is for the short timeouts. The other one is for the long timeouts. And what we see here is that for the short timeouts, CVC5's performance roughly constant, while Z3 has a significant drop here. And so that drop is caused by the change of an AST table. And each time when we spawn an instance of Z3, that table will be initialized, and it just got increased. And so this has been a big discussion on the Z3 issue tracker, and our tool could automatically detect this. For the longer timeouts, we see that Z3's performance is roughly constant, while CVC5's performance drops down. And this is mostly related to bit vector issues when with the transitions from CVC4 to 5. So in sum here, we can use ET to monitor performance regressions and changes in the SMT solver. I started this presentation with the observation that SMT solver should be correct and performant. And one way of ensuring correctness and performance is through doing SMT solver testing. And so there have been many papers or researchers who have done this, finding over 3,500 bugs. Due to this major effort by all these people, the crucial question that I asked in this talk is, have we tested enough? And so I first showed you why existing testers cannot give a satisfying answer to this question. And then I proposed a solution, ET, which is a powerful enumerative tester, which can tell us when testing is enough. And ET has many benefits, such as it produces super small bug triggers. And we then did a validation campaign, finding 100 bugs and showing the absence of bugs in the important theories. And we also showed significant, or we could also observe significant performance improvements when we investigated evolution. So ultimately, we can now answer the question, have we tested enough? Yes, since ET does not find bugs in the theories and solvers anymore. And so before I conclude, I want to shortly clear up with a quote of Dijkstra, who said, testing can be used to show the presence of bugs, but never show their absence. I actually disagree here, because we can use enumerative testers like ET to give us assurances of the absence of bugs. And we should just forget about what this old giant said. check out ET on GitHub. Maybe it can be useful for your research as well. And so we will extend ET soon to give us a more complete support for the grammars. And with that, I'm at the end of my presentation, and I'm happy to take any questions.
Questions? There's one here and one over there. Ilya first.
Thank you. Very bullish talk. So the dream of testing to kill verification once and for good. Anyway, so that's not my question. So you have referred to this Haskell Symposium tool. And if I'm not mistaken, the quick check community has been doing grammar-based property testing with completeness guarantees since, well, at least year 2000, but maybe for something like compilers from 2010 by the work by Palka and others from Chalmers. So, well, basically you did it for SMT Leap. How is it conceptually different from what property-based testing did in the quick check world? Can you please comment on that?
Well, I think the quick check works cannot handle context-free grammars. They can handle algebraic data types, which is a bit different. And as you said, I applied this to SMTlib, and I investigated the evolution of SMT solvers. I found many bugs, and so I think that's a contribution. I'm not claiming I'm completely or I'm not claiming I would basically subsume everything that they did before. I'm basically building off the shoulder of giants with this tool that with the Haskell tool that I built on. But yeah, I think I'm not fully claiming to have replaced what they have done in the Haskell community.
Well, I mean, I was under the impression that with algebraic data types, you can model context-free grammars because that's how we encode ASTs in compilers.
Yes.
So if you can generate arbitrary ADTs, then you can generate context-free grammars.
Yes, I certainly agree with you there. I'm just trying to make this make enumerative testing more accessible, being able to handle all kinds of grammars that are out there. And I've applied this to SMT solvers, as I said, and I see that as the main contribution of this paper.
Thank you.
And there's one more question here.
Yeah, well, very interesting talk. Thanks for giving it. I guess an implicit hypothesis in this slide is that the improvement in SMT solvers is due to this focus on enumerative testing. Correct me if I'm wrong.
We have found bugs with this tool, but I'm also using this tool ET to describe or to investigate the evolution that has been happening besides everything that we have done. Because I have stacked up releases from 2016 where even though there was no SMT solver testing. So in a sense, I'm doing empirical work there.
Totally. Yeah, I mean, so I guess I'm asking that question because we just had a keynote in which someone from Amazon came and told us about how they're running billions of SMT queries a day. And that also seems like something that would improve the correctness and performance of SMT solvers over time. So if you have any sort of empirical evidence that connects the improved correctness to the work in the enumerative testing community, that'd be amazing. So yeah, that's what I'll say.
One more question over here.
Hi, very nice talk. I really like the presentation. I'm Yuki from undergrad institution, and my question is kind of like, since you conclude that we already test enough for the SMT solver, I guess it's like what's next of like the future work of this?
So you're asking,
What's your future work?
what's my future work? Yeah, my future work will be twofold. Developing better SMT solvers, simpler and faster SMT solvers, and working more on making software making software testing more systematic.
Okay. If there are no further questions, can we please thank the speaker one more time?